Section 13.2, Gravitation and the Principle of Superposition. So we can find the net gravitational force by the principle of superposition, which is something that's applied to a number of areas of physics. And in short, it says that the net, the overall, is the sum of the individual effects. In other words, that you can just add up each of the individual effects to create an overall net effect. So, where you can add the individual forces as vectors, where we're just summing the force that particle 1 feels due to particles 2, 3, 4, 5, however many other particles there are, all the forces that F1 net overall will feel is just summing up all those forces. So this is much like chapters 5 and 6, where we found F net by summing up the forces. Key here, it is a vector sum. So the direction really does matter. So you have to pay attention to that. Keep our vector part straight. If you have a real extended object, right, where you're imagining that the object has all these different little mass elements, okay, how much does my fingernail create a gravitational attractive force? What about my knuckle, right? And so each of those pieces can be summed up to describe the overall force if you're doing then an integral. And we won't do that quite as much. One that we will use a lot, though, is if the object is a uniform sphere or shell. Based on the shell theorem, we can treat its mass as being at the very center instead, as being at that very point, and we don't need to worry about the extended object shape and do that full integral. So this is a fairly simple principle, but it makes a big difference in calculations. So let's try out a checkpoint. So the figure shows 4 arrangements of 3 particles of equal masses. Rank the arrangements according to the magnitude of the net gravitational force on particle M greatest first. Right, I want you to think about this, so please reflect. Go ahead and hit pause now. Okay, did you do that? Hoping so. Part B of the question is saying the figure shows an arrangement of 3 particles of equal masses. In arrangement 2, is the direction of the net force closer to A, the line of length capital D, or B, the line of length little d? So I want you to think on this as well. So come up with an answer to part A and to part B. You can pause to make sure to do that. All right, well, if we go back to part A and think about it, we know that the net gravitational force is going to be the sum of the individual forces. And so we notice in 1, the force that M feels due to the closer one is to the right, and to the further one is also to the right. So both of the forces are pulling the M particle to the right. So that's going to be pretty large. We noticed in 2, in contrast, one of the forces is to the right, but M is also going to feel drawn upward, right? And if we're adding forces that are at a right angle, they won't cancel, but they won't be able to fully add. It's going to be adding to get something that's not quite the exact sum or subtraction of the 2. And we'll see an example of this in just a moment. Notice 4 is much the same. We've rotated our arrangement from being like this to like so, right, in terms of where the particles are. But if we're just focused on the magnitude of the force, it's going to end up being the same. In 3, in contrast, M feels a force to the left as well as a force to the right. So now the forces aren't helping each other even slightly, they're actually acting against each other and subtracting from each other. So 3 is going to be the least amount. What about for question B, though, where we want to find the direction of the net force in arrangement 2? This one's a little tricky because I often want to think like, oh, big D, this one's bigger, so it's going to be a bigger amount of force. But we have to be careful here because we remember the gravitational force is inversely related to the distance between the particles, inverse square law to be specific. So the fact that little d is smaller means that it's going to divide out less from the overall force, and it's going to, the particle that's only little d away is going to produce a much larger gravitational force than the particle that is farther away. So we see that it is in fact none of the above for the answer to part A, because it's 1 is the biggest and then 2 and 4 are tied, 3 is the least. And then for part B, the net force is closer to that one, the particle that is closer to it, that line of length little d. Let's look at an example of this, summing two forces. The figure shows an arrangement of 3 particles, particle 1 of mass 6.0 kilograms, particles 2 and 3 of equal masses of 4 kilograms, and distance A is 2.0 centimeters. What is the net gravitational force, F1 net, on particle 1 due to the other particles? I'm going to encourage you to take some time to jot down a picture, write down what you know. I'm going to do the same, and we'll compare notes in just a moment. So go ahead and hit pause now. All right, so I drew my picture. I wrote down our knowns, what we want to know, F net due to particle 1. I even jotted down tools, hopefully you did too, that, hey, we have our Newton's law of gravitation. F vector is equal to G m1 times m2 divided by r squared in the r hat direction, as well as our law of superposition, principle of superposition, that says F net on 1 is equal to the sum of the forces on 1 from 2 up to n particles. Here it will just be 2 and 3. So we can even write this, that for this particular case, F net on 1 vector is just going to be equal to the force of 1 that 1 feels from particle 2 vector plus the force that 1 feels from particle 3 vector. So the vector part does matter, and before I get too carried away with plugging and chunking numbers, I do want to think about the direction of the forces and maybe the rough magnitude, right? So if I think about particle 1, what direction of force will it feel due to particle 2? You can point with your fingers. And I think some of you are pointing up. I'm going to trust that you are. Yeah, so particle 1, we draw it as being pulled up. That would be the force of 1 from particle 2. And now what about the direction of the force that particle 1 feels from particle 3? Point with your fingers in the direction of the force. Yeah, it would be towards particle 3. Now what about relative magnitude? Well, remember, because it's farther, it is going to be a smaller magnitude. So I'll jot that in. It's not going to be to scale, but I'll at least try and help myself remember that I expect to get a smaller number for the force that 1 feels from particle 3. All right. So that's useful to have. Before we get into adding these up, I'm going to calculate the magnitudes of them, and then we'll come back to the directions. So the magnitudes can be calculated with this equation. So F1 due to 2 is equal to G m1 m2 divided by the distance between them, between 1 and 2, which is just distance A squared. So in terms of magnitude, that is now sufficient, and we can start plugging and chugging. So 6.67, and please do include that 7, because you can make a big difference here. So newtons meter squared per kilogram squared times mass 1 is 6 kilograms, times mass 2 is 4 kilograms, and then divided by, I went ahead and wrote my centimeters, it's 2 centimeters in meters as 0.02, because I don't want to get off by factors of 10. I'm going to divide by 0.02 meters squared. All right. Now we can plug and chug. 6.67 EE11. The EE button is a wonderful one on your calculator if you haven't used it before. Times 4 times 6 divided by 0.02 squared. Right. And we get this fairly small number. 4.00 times 10 to the 6. 10 to the minus 6 with what units? We can double check, right? Because of the units here, the kilograms will cancel out, the meters will cancel out, and we're just left with the units that we expect for a force, newtons. So that's the force on 1 due to 2. We can do the same thing for the force on 1 due to 3, and we can even save ourselves some calculations if we notice that because they have the same mass, the only thing different about particle 3 is that it's further, and it's twice as far away to be exact. So that allows us to do a neat trick to save ourselves a little bit of calculator effort. So force of 1 from 3 is much the same as this. I'll write it out even. So G M1, M3, divided by 2A, and be careful, the 2 and the A are both squared. So that's something worth noting. M3 we could rewrite as M2, and I'm going to pull the 2 squared out, so that I have 1/4 of G M1, M2 all over A squared. That's something we've already seen before. That is exactly the same as what we had up here. So that means I could plug in here with my force 1 of 2, what I already calculated. In other words, my 4.0, I'm just going to take 1/4 of it, and it cancels out. Because this is just F1 on 2. So we get that this is 1/4, I'm still on the screen for now, of 4.00 times 10 to the minus 6 newtons. And so that'll just be 1 times 10 to the minus 6. So F that particle 1 feels due to particle 3 is 1.00 times 10 to the minus 6 newtons. So we have both of these results, but it's not what we're ultimately solving for, right? It's asking for the net gravitational force, not the force on each of them. So we need to add these together, and we can't just add them 4 plus 1 equals 5 because they're not in the same direction. So how do we add vectors when one's pointing up and one's pointing at a right angle to it? Well, this is where we can make our triangle again, right? So I'm going to draw these vectors a little bit bigger so that we can see. So F1, 2, F1, 3, and we can say, hey, if I moved F1, 2 to the side or F1, 3 up, then my net force is just going to be the diagonal of these. F1 net. So drawing it over here so we can see the full triangle effect, I can draw my F1, 2 over on the left. So then how do we combine these two individual in the x and the y directions to get the net? It's going to be our Pythagorean theorem. And that will then get us the right result. So we're going to get a little bit low down here. I think we'll be able to do it. F1 net is equal to, since it's a squared plus b squared equals c squared, I'm taking the square root of a squared plus b squared. So the square root of F1, 2 squared plus F1, 3 squared. So 1 squared plus 4 squared, the 10 to the minus 6 can come out in front. And we get the square root of 17, where the 10 to the minus 6 will just come out. So it ends up being 4.12. Times 10 to the minus 6 newtons. All right. So that gets us the magnitude of the force, which is great. And it's often all that's needed, but sometimes they also want the direction, which I just realized the screen was extra small, so I'm sorry. Now the screen is a bit bigger, so hopefully you can see everything that was going on there. You can go ahead and pause to see any parts of it. All right, now what about the direction? Well, for the direction, coming back up here, that's usually going to be the angle, and we often define it relative to the x-axis. So in my picture up here, I would want to be able to specify that angle phi. And so to get that angle, I can use tangent. So I think I can fill it in right here. Tangent of phi is equal to f(1,2) divided by f(1,3). And if we take the inverse tangent of that, then we get our result, where we have the inverse tangent, the opposite over the adjacent, 4/1 effectively, because the 10 to the minus 6 will cancel. All right, so putting in 4 and inverse tangent, and that comes out to 76.0 degrees. And as long as you label what angle you solved for, that's sufficient. You could also argue that it would be even better to specify the angle from the positive x-axis, right? If the positive x direction is over here, then the full proper angle would be 180 minus phi. So 180 minus 76, which would just be 104. So that's what I would call theta technically. So 104 degrees, but I would accept either of these, again, as long as you're clear which one you've calculated. You could even calculate the angle between F1 net and the vertical, but that one you really need to label that it's there. If you want to find the full angle, then you would only add 90 to that. All right, so that pulls us through this example. Sorry I didn't share the screen sooner, but the slides do at least have a visual of each of the steps here of finding the force due to each of the particles and then summing them up to find F1 net, as well as getting the angle as either 76 degrees or 104 degrees. So either of those works for me. All right, that brings us through 13.2. Please feel free to ask any questions as you have them.